Hello class, today's topic is on vectors. A vector is a mathematical construct that has both a direction and a non-negative magnitude. A good example of an application of a vector is a force, because a force both has magnitude, the amount of force, and it also has a direction, the direction in which the force is exerted. A mathematical construct with a magnitude only is called a scalar, and think of something like the mass of an object. You can measure the mass of an object and give it a magnitude, but it doesn't necessarily have any particular direction. Now, vectors are graphically represented as arrows, beginning at the tail and ending at the head, or sometimes people simply say the starting point and ending point, and whose length represents the magnitude of the vector. Typically, vectors are symbolically represented as bold letters or letters with an arrow accent, such as this bold V or this V with an arrow above it. A two-dimensional vector has directions limited to a two-dimensional plane, and a three-dimensional vector has directions limited to a three-dimensional space. Now, the magnitude of a vector is represented by, you put the vector symbol inside what looks like absolute value signs. Now, determine the magnitude of each two-dimensional vector depicted below. So we have two different vectors, u and v. Normally, you would want to make this u be bold or put a little arrow above the u. Now, the length of each arrow segment is going to be its magnitude. Now, the easiest way to find the magnitude is to make a right triangle and then to use the Pythagorean theorem to find the length of the hypotenuse. So we can see if I make a right triangle out of this, we have a horizontal length here that's 5 units, and then a vertical length here that's 2 units. So the magnitude of this vector is going to be, and the Pythagorean theorem would give us the square root of the sum of the squares of the two legs, so 5 squared plus 2 squared. And this gives us the square root of 25 plus 4, which is the square root of 29. The other vector v, so one leg is 1 unit long and the other leg is 3 units long, so the magnitude of the vector v will be the square root of 1 squared plus 3 squared. That's going to give me the square root of 1 plus 9, which is the square root of 10. Let's go to the next page. If the tail of the vector were situated at the origin, then the vector can be represented by the coordinates of the head of the vector in angle brackets, called the components, such as bracket a comma b bracket. So these vectors aren't really positioned in such a way that the tail is necessarily at the origin. In fact, you want to be very flexible. If you shift this vector u to another location in the xy plane, it's still going to be the same vector, as long as it has the same length and points in the same direction. But if we were to make some axes and make it so that the tail of vector u is at the origin, then where would the head of the vector be? Well, from the origin, we go right 5 and we go up 2. So this point would be the point 5 comma 2. And so we can say that the vector u, one way to represent it is to say that it has components 5 and 2. And we put them in these angle brackets. Now, it doesn't really matter. We would still say that that vector has components 5, 2, even if it originated somewhere other than the origin. Now, if we do a similar shift for vector v, put the origin at its tail, which would be right about there, and the head of this vector v would now be at this point right here, which given this frame of reference would be at -1, 3. And so we can say that vector v has components, use angle bracket, -1, 3, angle bracket. And again, you would still say that this vector has these components, even if the frame of reference were shifted there. In fact, one good way to think about the components of a vector is to not even think about where the origin is, but use some ideas that you would use in calculating the slope of a line, like rise and run. So if you were to start at the tail and then you wanted to calculate the run, well, the run here would be +5 because you go to the right 5 units, and then the rise would be +2. So you would say that this vector has components 5, 2. Same thing with this one down here. Just think run and rise. Well, we'd have to run to the left 1 unit, and then we'd have to rise a +3 units, and so the components of this vector are -1 and 3. A magnitude of a vector, let's let w be a vector, AB. The magnitude of this vector is going to be the square root of the sum of the squares of the components. Even if the components are negative, the squaring will get rid of that negative. Okay, let's go to the next page. The direction of a two-dimensional vector is the angle between the vector and the positive x-axis, and is in the range from 0 to 2 pi. So determine the direction of each vector below. Assume again that the tail is at the origin, if you will, and we have the positive x-axis going off this direction. The angle we're looking for is this angle here. We'll call this theta. The components of this vector were +5 to the right and then +2 up. The tangent of theta would be equal to the opposite divided by the adjacent. If you recall, the arctangent function gives us angles between negative 90 degrees and 90 degrees. So theta would be the arctangent of 2/5. Type in arctangent of 2/5. This is giving me an answer not in degrees, but in radians. If you want to switch to degrees, then click the wrench sign in the top right corner, and then select the degree option. And it gives me that angle in degrees. And let's go ahead and give it an answer rounded to the nearest tenth, so to 1 decimal place. So this would be 21.8 approximately degrees. And we want to make sure we give an answer that's in this interval. Now this interval is mentioned in radians, but in degrees it would be 0 degrees up to 360 degrees. Now for the vector v, if we put the origin at the tail of vector v, then the head of vector v would be at the point -1, 3. So the adjacent would be -1 and the opposite would be 3. The angle we're after is this angle right here. Let's call this alpha. And we know again that the tangent of alpha will be equal to 3 over -1. However, alpha is going to be a second quadrant angle. And notice what happens when I use an arctangent to get alpha isolated. We do an arctangent of, this is just -3, and I get an angle -71.6 approximately degrees. This is an angle that's pointing into the fourth quadrant, because negative angles are clockwise. We want the comparable angle that points into the second quadrant. So we just need to rotate 180 degrees. So if I add 180 to this figure, it'll give me the correct angle I'm after. So this would be 108.4 degrees approximately. So recognizing this, I have to put this 180 degrees here in my calculation, and now I can say that alpha is about 108.4 degrees. Okay, let's go to the next page. The opposite of a vector is another vector with the same magnitude but opposite direction. This notation right here stands for what's called the opposite of a vector. It's the negative of the vector v. Now, what's going on here in this case is, let me go ahead and redraw vector v. I made a line segment. Vector v with points in this direction. Keep in mind that no matter where I move this vector, we can call that still vector v because it has the same direction and the same length. But when I do the opposite of this vector, all I really have to do is keep the length but change the direction. So this vector here would be the opposite of vector v. Now to figure out what its components are, so you have this negative sign, and then the components of v were -1, 3. So when you're doing the opposite of a vector, you simply distribute to both components. And so our vector becomes instead 1 and -3. This makes perfect sense because if you're looking at negative v that's in our image here, the starting point, then you would have to go right 1 and then down 3. Hence the components of this are 1, -3. Also, vectors can be scaled by positive scalars to change its magnitude without changing its direction. So an example of that would be something like 2 times vector v. Let's go ahead and just do this numerically first. If we're doubling a vector, then you wind up just doubling all the components of that vector. And so we would get -2, 6 would be the new components. And visually over here, what would happen is we would take vector v and do 2 copies of it back to back. This vector right here is twice the vector v. I'll put it somewhere kind of out of the way. It's a vector that has the same direction as v, but its magnitude is twice what it used to be. You can even scale by factors less than 1, for example, 1/3 of v. So if you were to take a look at vector v and break it into 3 equal pieces, those breaks would be here and here, and this vector right here would be 1/3 of the vector v. And again, it's always 1/3 of vector v, no matter where it starts. Numerically, we just do 1/3 of vector v, we distribute and multiply, so we wind up getting components -1/3, 1. Scaling by a negative scalar will scale its magnitude and also result in a vector going in the opposite direction. So we're seeing something like that for this last case. We do -2/5 of the vector u, so we're going to wind up with a vector that's 2/5 as long as vector u, but also in the opposite direction. You could sort of eyeball this and try to break this up into fifths and then just keep 2 of those. You can also make a similar triangle. So if we go to the right 5 here for the vector u, then I'm only going to want to go right 2. That would be 2/5 of 5, and then go up to there. And so this vector right here, this is 2/5 of u. But we want -2/5 of u, so not only do we have to change its magnitude, but then also change its direction. And so this vector is -2/5 of the vector u. Find the components of this new vector by doing -2/5 and multiplying that by each of the components of the vector u. And the components of the vector u were 5, 2. So do -2/5 times each of these. -2/5 of 5 is just -2. And then -2/5 of 2 is -4/5. Okay, let's go to the next page. Adding or subtracting vectors is as simple as adding or subtracting corresponding components. Given the vectors a and b below, Draw and give the components of the vectors that follow. All right, first of all, we have two vectors being added, vector A plus vector B. Let's go ahead and find the individual components of these two vectors. Vector A would be you go to the left 3 units, and then you would go up 1 unit. Then the components of vector A are -3, 1. And to this, we're going to add the vector B. Starting at the tail, we would go left 1 unit and then down 2 units. So its components are -1, -2. We combine two vectors, we add them by simply adding corresponding components. So -3 plus -1 is -4, and then comma, and then 1 plus -2 is -1. Now visually what's going on when you add two vectors is the following. Start with the vector that's first mentioned, so vector A, and you position at its head the tail of the next vector, which is vector B. So I'm going to draw vector B again, relocate it so that its tail is at the head of A. A plus vector B is going to be a new vector that starts at the same place where A starts, where the head of the vector is going to be where the head of vector B is, after A and B are put one after the other like this. This right here is the vector A plus B. And look what its coordinates would be. We would go left 4 and then down 1. And you can see that's exactly what the components are we got simply by adding the components of vectors A with the components of vector B. Once you have this established as this vector, it doesn't really matter where you put it, it's always going to be vector A plus B. Okay, let's do vector A minus vector B. Right, vector A, its components, and then minus, and then vector B. And then here you do the same thing, but you just make sure you distribute the negative and then combine. And so we have -3 minus -1, that's -3 plus 1, which is -2. And we have 1 minus -2, which is 1 plus 2, and we get 3. So these are the components of the vector that's produced when you do A minus B. And also you can think of A minus B as really just doing the vector A plus the opposite of the vector B. So that's how I'm going to think about it when I actually draw the vector over here. I'm going to first begin by drawing the opposite of vector B, and then I'm going to add this to the vector A. So let me get this vector out of the way. And so this is the opposite of vector B. And when I do vector A and then tack on to the end of it vector -B and then add them, I'm going to get this vector here. And now I can erase the opposite of vector B, and we can call this vector here vector A minus vector B. And notice what its coordinates would be. We would go left 2 and then up 3. And again, once you have it established, it doesn't really matter where you put it. Now we're going to do vector A plus twice vector B. We start by writing vector A, and then we add to this twice vector B. Then you double the components of vector B, and then add these to the components of vector A. 2 times -1 is -2, and then add that to the -3, and we get -5, comma. Right? And now we do 2 times -2 right there, and we get -4, and we add that to this 1, and we get -3. Let me move this back out of the way. I'm going to begin by finding what twice B is. Here's one copy of B, and then a second copy we'll just tack on to right here, so we can really just make this now be twice as long as it used to be. And here's the vector 2b, and I've positioned it so it starts where A ends. And then this long vector is our sum vector. I can erase vector 2b. This is vector A plus twice vector B. And look at what its components would be. We would go left 5 and then down 3, so -5, -3, exactly as we calculated earlier. And once again, it doesn't really matter where I put this. It's always going to be the vector A plus 2 times the vector B. All right, and then let's do this last one. We have 1/3 of vector A, and we're going to subtract 1/2 of vector B from this. Distribute the fractions. So you have -1, 1/3, plus, and distribute the -1/2. So -1/2 times -1 is +1/2, and then -1/2 times -2 is +1. And now I just continue with adding the components. -1 plus 1/2, that's going to be -2/2 plus 1/2, that's -1/2. And then 1/3 plus 1 is 1/3 plus 3/3, that's going to be 4/3. And then visually what's going on here, let's start with 1/3 of vector A. So this is 1/3 of vector A, I'll position it there. Here's 1/2 of vector B. We wanted to subtract 1/2 of vector B, so we actually need to change the direction of this second vector I made, and then reposition these. So here is 1/3 of vector A, and here's the -1/2 of vector B, and when I add them together, we get this new vector right here. And once that's done, let me go ahead and erase the other vectors, and this here is our vector that is 1/3 of vector A minus 1/2 of vector B. And its components are -1/2, 4/3, suggesting that from its tail, we would go left 1/2 and then go up 4/3. And again, doesn't matter where I position this. Okay, let's go to the next page. The dot product of two two-dimensional vectors is a scalar calculated in the following way. So we have vector u, and then we say dot product with vector v. So u dot v, and here are the two components of u and the two components of v. And when you dot the two vectors, you wind up multiplying corresponding components and adding the result. And you wind up with a scalar. So this in the end is going to be a single number. Find the dot products below. So we multiply the corresponding entries. So I multiply the two orange numbers basically, and we get -2. And then I'm going to multiply the second component, so the two green numbers. So we get -2 plus 6, and we get 4 is the dot product. In the next case, let's do 2 times -2, that's -4. And then to this we're going to add, and then -3 times 0 is just 0. So we get a negative number this time, -4. And in the last case, we do 3 times 2, which is 6. And to this we add, and we do -2 times 3, and we get -6. And 6 plus -6, and we get 0. Your dot products will be positive, negative, or 0 are the possible results. Okay, let's go to the next page. Suppose theta in the range from 0 to pi is the angle between two vectors when their tails are in the same position. The following equation relates this angle to the dot product. So we have two vectors, u and v. Here's their dot product. Here are their magnitudes times the cosine of theta, where theta is the angle between the two vectors. So we're not going to prove this statement. We're just going to learn how to use it to find the angle between two vectors. Notice all three of these pairings are the same pairings of vectors we had on the previous slide. And let's go ahead and graph them so that they have the same tail. So the first vector is -2, 2. So we go left 2 from the tail and then up 2. And then the other vector v is right 1, up 3. Now whenever you have an angle like you see produced here, there are always two different angle measurements. So you could do an angle measurement, the longer one that goes around like this. Another option, a shorter angle measurement. And the red and the green angles, when added together, should give you 360. Now the angle in question that the formula is referring to is the shorter of these two. It's always the angle that's in this interval right here, which is from 0 to pi, which is 0 to 180 degrees. So the red angle is not of interest. We're trying to answer the question, what is this green angle? That's the theta. Let's go ahead and graph all pairings, and then we'll talk about how to find these angles. So this next pairing, we have the vector 2, -3, so let's go right 2, down 3. And then vector b is left 2, and then up, down, nothing. Now the angle that we're interested in is a smaller angle right here, so this is the theta. And then our third pairing, we go right 3, down 2, and then for vector z, we go right 2, up 3. And again, we are after this angle right here, theta. Okay, now this formula, we're going to actually solve it for theta. So the very first step, of course, would be to divide both sides by these magnitudes. And so this tells us that the cosine of theta would be equal to the dot product of u and v divided by the product of their magnitudes. And then the final step would be to arc cosine both sides. So theta will be the arc cosine of this expression. So let's go ahead and do that over here now. So theta is equal to the arc cosine, the cosine to the -1 of, and then we're going to do the dot product of these two vectors. We've done this already, but it's going to be -2 plus 6. This was the positive dot product. So we got a 4 up top. And then divide this by the magnitudes of these two vectors. To find the magnitude, you square the components, add them together, and then take the square root. So we do -2 squared, which is 4, plus 2 squared, which is also 4. That's 8, and then take the square root. So we get radical 8. That's the magnitude of vector u. And the magnitude of vector v comes next. It's the square of 1 plus the square of 3, so that's 1 plus 9. And then take the square root, so square root of 10. Now the inverse cosine is an inverse trig function that is already programmed to return angles between 0 and pi, which is exactly the kind of angles that we're after. So going over to Desmos, I've already typed this expression in. Make sure you're in degree mode, which I am. And this gives us 63.4 degrees approximately. Which you can look at this picture, that makes sense. It's less than 90 degrees. This is an acute angle, meaning it's an angle between 0 and 90 degrees. Now in the next case, our theta will be the arc cosine of, and we're going to do the dot product of these two vectors. So we do 2 times -2, which is -4, and add that to 0, so we just get -4, and divide that by the product of the magnitudes. The magnitude of A, square 2, square -3, so that's 4 and 9, add them together, we get 13, and take the square root. Do the magnitude of vector B. Now vector B's magnitude is quite easy because it has no vertical component. Its length is clearly 2. But if we did the formula still, we would square -2 and get 4, square 0 and get 0, and add them together and get 4, and then take the square root. Well, that just takes me right back down to 2. All right, now let's go over to Desmos. So we get 123.7. This is more than 90 degrees, which makes sense in our picture. This is an obtuse angle, meaning it's between 90 and 180 degrees. And then our final case, theta will be the arc cosine of, and then the dot product of these two vectors. It was 6 minus 6, or 0. The magnitude of the vector w will be 9 plus 4 inside a radical, so 13. And the magnitude of vector z will also be square root of 13. But the 0 divided by this number is still going to be just 0. So we just have to do an arc cosine of 0, which we really don't need a calculator for, because here we're trying to find the angle between 0 and 180 degrees, where the cosine is 0, and that angle is 90 degrees, suggesting this angle here is a right angle. In such a case, we say that the two vectors are perpendicular, or we can use the word orthogonal. So So we say vectors w and z are orthogonal, or you can also just use the word perpendicular. Now step back and take a look at all three of these. When the dot product was positive, we wound up doing an arc cosine of a positive number, which gives us an acute angle. When the dot product was negative, we did an arc cosine of a negative result, and that's going to give me an angle in quadrant 2. So that's a quadrant where cosine is negative. And so that gives me an obtuse angle. And when the dot product is 0, that gives me arc cosine of 0 overall, which is 90 degrees. So the dot product is useful for establishing a few things about vectors. Okay, let's go to the next slide. For three-dimensional vectors, the magnitude and dot product are as follows. Furthermore, scalar vector multiplication and vector addition and or subtraction are similar to the two-dimensional case. So there really isn't anything new. Everything just extends from 2 to 3 dimensions. So if you want to find the magnitude of a vector, then you wind up squaring all the components of the vector, adding them together, and then taking the square root. If you want to do the dot product of two vectors, then you multiply corresponding components and then add the results. Now we have two different three-dimensional vectors here. I'm no longer going to do graphing of these vectors in our notes, although I will go over to a three-dimensional program called GeoGebra 3D and input these vectors just for the sake that we can see what they look like in 3 dimensions. Okay, so here we have GeoGebra 3D. We get a three-dimensional space that we can rotate. Now the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis, the third dimension. The gray plane you're seeing is called the xy plane. And if you look straight down the blue axis, just like this, then you see what we're used to seeing with just the xy plane. Now, to type in vectors in GeoGebra 3D, you just type in a letter, like you see up here. I typed in U, and I started some parentheses, and I typed in 3 coordinates, and ended the parentheses, and it defaulted that to making a vector, which I'm going to reveal now. So this vector U is created by going, so if I look just at the xy plane, look where that vector is pointing, right 2, up 1. So the x-coordinate is 2, the y-coordinate is 1, then we go down 2. So if I look now at the floor of the side, just like this, you can see that the head of the vector is down 2 units. So you put all those together, you get this vector that's pointing in 3 space that I'm just kind of rotating around to see it in different angles. The other vector v, I'm going to reveal as well. So here's the 2 vectors. Vector v has a positive z coordinate, so it means its head is above the floor. So these arrows, they also have magnitude, and they also have a direction. And if you do their dot product, you can use the dot product to again find the angle that's between them. So 3 times vector u, well here's vector u, let's triple it. Just triple all the components. So triple 2 is 6, triple 1 is 3, and triple negative 2 is negative 6. This would be the components of triple u. And the result would be a vector that points in the same direction as u, but is 3 times as long. If we do u minus 2v, I'll write u down first, and then minus, and then I'm going to go ahead and just double vector v. It gives me 6, 0, 4. And then I subtract component-wise. So I get a new vector. 2 minus 6 is negative 4. 1 minus 0 is still 1. And negative 2 minus 4 is negative 6. The dot product of u and v. So we multiply corresponding entries. So 2 times 3 is 6. Then we do 1 times 0 is 0 and add. Negative 2 times 2 is negative 4. So we add these together and we get a positive 2 out of this. And because the dot product is positive, we know that the angle between them is going to be acute. The angle between these 2 black vectors that you're seeing here, the angle between them is less than 90 degrees. All right, the magnitude of u, so we square all the components of u, add them together, and then take the square root. So it's going to be the square root of 2 squared is 4, plus 1 squared is 1, plus negative 2 squared is also 4. So we wind up getting 9 inside the radical, so we get just 3. The other vector, square root of, square the 3 is 9, square the 0 is 0, square the 2 is 4, and we get radical 13. Now the angle theta is going to be the same formula we used in the past. This is the angle between them. So we do the arc cosine of, and we do their dot product, which we did already, got 2, and divide by the product of their magnitudes. So 3 times radical 13. And then we reach for Desmos to calculate this. And we have 79.3 degrees. Okay, in the final slide, the cross product of 2 three-dimensional vectors produces a 3-dimensional vector that is perpendicular to both vectors and is calculated in the following way. What you're seeing here appears to be a 3x3 matrix, which I hope you've seen in your recent past in a college algebra course. And the fact that the matrix has what appear to be absolute value bars means that we're finding its determinant. The first row of this matrix are 3 vectors, I, j, and k. The vector I is the vector that has a 1 in the first component and then zeros for the others. The vector j is the vector that has a 1 in the y position and zeros everywhere else. And the vector k is a vector that has 0 in the x and y but 1 for the z. And we use what's called cofactor expansion to do this calculation. Let me actually do a specific example of this using the two vectors that we've been working with. So vector u cross vector v, in this case, is equal to, and I'm going to write a 3 by 3 matrix where I put vectors I, j, and k along the first row. Then I put the vector u, its components, in the second row, and then the vector v's components in the third row. And then we do a process called cofactor expansion. We first sort of target this I. We write the I down, and then next to it, we do a calculation of a determinant of a 2 by 2 matrix that's not currently crossed out. So this 2 by 2 matrix right here. The next thing we do is move our target practice to the j. And once it's there, the j is in a negative position. So when you do cofactor expansion, you should alternate signs. We go negative vector j times, and we put a 2 by 2 matrix here that is the 4 numbers not currently crossed out. So that's going to be 2, -2, 3, and 2. And then we do this one more time, move our target practice to the k. The k is back in a positive position. We alternate signs. So plus vector k times the 2 by 2 determinant that's not currently crossed out is 2, 1, 3, 0. So I'm hoping you've seen cofactor expansion before, but if you haven't, there's a little brief intro on it. You're just going to have to know this process for calculating a cross product. So we have a vector I times, and we do a 2 by 2 determinant right here. To do a 2 by 2 determinant, you multiply the diagonal entries and then subtract the other product. The 1 times 2 gives me a 2, and then subtract, and we do 0 times -2. That's just 0, so subtract 0. Then we subtract the vector j and do a 2 by 2 determinant here. So we do 2 times 2 is 4, and then 3 times -2 is -6, but we subtract that, so it becomes +6. And then finally we say plus k. 2 times 0 is 0, and then minus, and we have 3 times 1 is 3. So in the end, this winds up being 2 times vector I minus 10 times vector j minus 3 times vector k. Vector I is 1, 0, 0. Vector j is 0, 1, 0. And vector k is 0, 0, 1. So in the end, we really just wind up getting 2, -10, -3 as our final vector. So this vector, 2, -10, -3, is called the cross product. So let me type that in as a brand new vector. We'll call it w. So I'll say w equals 2, comma, -10, comma, -3. And that makes this new vector w. It's the longer of the two vectors that we're seeing here. It makes a new vector, but what's significant is that this new vector is perpendicular to both of the original vectors. So if I try to change my perspective so that I line up the other vectors, you can see that the new vector here is perpendicular to both of them. Here's another angle where we can kind of see that. The new vector is perpendicular to both of the original vectors. All right, this wraps up our introduction to vectors